All right, in this lecture, we're going to take a look at the concepts of molecular shape and polarity. So we're going to take a look and see how different molecules can be classified according to their shape that they take in 3 dimensions. And then we're also going to take a look at polarity. Polarity means molecules that are going to have 2 poles, or a positive and a negative end. And those are going to have to do with electronegativity, and shape also is going to help us figure out the polarity of molecules. So let's get started. Domains. Ooh, the heck? So in the early part of this chapter, we were introduced to the Lewis model, or Lewis dot structures, which is a way to kind of picture how covalent bonding works. We represent the valence electrons as dots, and then with those dots, we arrange them and see how bonds are being formed between 2 atoms. So we can use those Lewis dot structures that we've been learning how to draw in combination with a concept called VSEPR, V-S-E-P-R. Chemists just pronounced that VSEPR. Anyways, we can use the Lewis dot structure and VSEPR to predict these shapes of molecules. Now, VSEPR stands for valence, shell, electron, pair, repulsion. And basically what it means is that it states that electron groups, so those dots that we have in the Lewis dot structures, right? So the electron groups are going to want to basically be as far apart from each other as possible. All right. When we have 2 electrons that are paired up with opposite spins, they are going to repel any other paired electrons that have opposite spins. And so that repulsion in the valence shell is going to set up different types of geometries or shapes of molecules. So for example, in this first one here, these little balloons kind of represent the 2 electrons that are in each of those kind of subshells in the valence shell. Okay, so these balloons represent those electron groups, and they want to be as far apart from each other as possible. So if we have 4 electron groups around a center atom, so in the balloon model we can't quite see carbon, but carbon's here in the middle, and we've got 4 groups of hydrogens bonded to them. And so in order in 3 dimensions for all 4 of those H's to be as far apart from each other as possible, they're going to come in an angle at 109.5. Okay. Now the second one is also shows the VSEPR model, but here this here is a lone pair. This is a for example, when you do the Lewis dot structure for nitrogen, right? Nitrogen has 5 valence electrons, so we do the first 4, and then we pair that last one up, and this is a non-bonding pair. Okay, so non-bonding pairs of electrons also want to be as far apart from other electrons around that center atom. So this top thing here represents the non-bonding pair of electrons, and then again the balloon-looking things underneath is representing those bonded pairs between, in this molecule, the nitrogen and hydrogens. Okay, so because that bonded pair up there wants to be as far apart from those bonded pairs as well between the nitrogen and hydrogens, we're going to end up getting a distance, okay, between the hydrogens of 107 degrees. Okay, so and that's because the bonded pair, the non-bonding pair, actually takes up more space. They kind of hog more space around the electron, or around the central atom than the other electrons. Okay, so that's why we see that this degrees is a little bit less than the other one with that 4th hydrogen up on top instead of a bonded pair. Okay, so let's go ahead and start diving into what this looks like in terms of molecular shapes. And I'm noticing that when this integrated into my program, it kind of is covering up some of the words here. So on Canvas, you'll see that I do have the PDFs for the lecture notes, so you can get the full wording from those PDF files, all right, because it looks like some of these are a little overlapped, but that's okay. All right, so let's take a look at the first shape. The first shape is what we call linear. It's the repulsion of two electron groups around a central atom, and it results in a bond angle of 180 degrees. So this little O should be on top there, 180 degrees, okay? Just like a straight line has a angle of 180 degrees, okay? So if we look at CO2, right, CO2 has a center carbon atom, and this carbon atom only has 2 electron groups. That means there's only 2 sides of this carbon that have electrons in it, because remember, he's doing a double bond here. Okay, so he's sharing 4 electrons. 3, 4. There you go. 4 electrons, okay, on either side. So he does not have any lone pairs or bonded pairs on top or bottom. So he only has what we call 2. He has 2 domains. I don't know what's going on here, but that's okay. 2 domains, okay, 4 electrons, meaning 2 sides. So when you've got 2 sides for electrons, this is a linear shape, and you're going to see a bond angle again of 180 degrees. Okay. All right. So this is what this one here on the left is what it looks like, when we basically drawing out like the Lewis dot structure. Over here, we call these space filling models, meaning, when molecules are actually put together, and you've got, the electrons surrounding all the atoms that are filling in that space. Okay, that's what that looks like. So in both of these, they have a straight line. There's nothing coming out from either top or bottom or any crooked sides or anything like that. It's just a straight line in the middle. So we call that a linear geometry. Now the second shape that we're going to talk about is trigonal planar. Okay, trigonal planar results when there are 3 domains, 3 electron domains. So that means that center atom has 3 sides. So I'll put domains/sides. So 3 sides that have electrons on it. And if we're trying to get those electrons to be as far apart from each other as possible, we're going to end up with a bond angle of 120 degrees. And this is what we call a trigonal planar geometry or shape. Trigonal means triangle, okay, and planar means flat. So we can see from this picture here, okay, that it literally looks like a flat triangle, right? So flat little triangle right there. Nothing sticking up, nothing sticking down. It's just a flat little triangle. So we call that a trigonal planar. So when we talk about these shapes, we're going to start from the simplest shape, the linear shape, because there's only 2 electron groups around the center atom. All right, then we've added a 3rd electron group around that center atom. All right, and that's given us the trigonal planar shape. And now let's take a look if we add another electron group. All right, so when we add another electron group, a 4th group of electrons around that center atom, we can actually get a couple of different shapes, all right? And that's because we could either have all of those electron groups being bonded pairs, or some of those can be lone pairs. Remember, like I'd mentioned before in NH3, remember nitrogen, right? When you do his Lewis dot structure, he has that lone pair, that pair of electrons that does not bond. And I mentioned before that guy, those, non-bonded pairs also want to take up more space. In fact, they hog even a little bit more space than the bonded pairs. Okay, so let's see how the rest of these shapes pan out. All of these shapes, you'll have 4 electron domains. Okay, but some of them might be bonded pairs and some of them lone pairs. Okay, so the first one that we're going to take a look at is tetrahedral. Tetrahedral shape comes from the result of having 4 electron groups or 4 domains, and all of them are bonding pairs. That means we have just like in this picture, an atom bonded to all 4 sides of that center atom in the middle. Okay. So this is, when they want to take up as, much space as possible and kind of push everybody else out, we end up with a degrees, an angle between the atoms there, okay, of 109.5. Okay. So at that angle, all of the atoms that are bonded to that center atom are as far apart from each other as possible on all sides. Okay, so we call that a tetrahedral. Again, 4 domains. Okay, and all of them are bonded. So if we did the Lewis dot structure, let's just pretend that this is CH4, right? So we would have C in the middle, and then we'd have the 4 H's all around. So on paper, tetrahedral kind of looks like a cross, okay? In 3D, it looks like this, funny looking shape right there. Okay, but like I said, we're going to do all of our practice on paper. So in 2D, it's going to look like, this cross or T shape. T for tetrahedral. Okay, so that's if we have all 4 sides of that center atom bonded to a different atom. Okay, but let's take a look at the next one. The next one is what we call trigonal pyramidal. Okay, we've seen that word trigonal before. In the last slide, we said trigonal planar is where we had 3 bonded pairs. And so that kind of pans out to be a flat triangle. In this one, we have 4 electron groups. So we still have 4 domains, right? So if we're taking a look at this picture over here on the right, this non-bonding pair of electrons is one domain, and then all these B's are the other 3. So we still have 4 sides around the A atom in the middle that have electrons, but we can see that one of them is a lone pair. Okay, so this one right here is the lone pair, and then we've got 3 atoms that are bonding to it. So when we take a look at a molecule in kind of a 3D shape, we are not going to see the bonded pair. Okay, so that's why up here we don't have a little, thing up here with the bonded pair on it, because you're actually not going to see that in an actual, molecule when it's built. Okay, what you'll see is just like this. Okay, so this is what we call a trigonal pyramidal geometry. So it is, again, it's a triangle, but the middle is kind of popped up, okay, like a pyramid almost. Okay, so think of like, if you did like a I forget how you, the geometry shape, where it's like a cylinder but a pyramid. That's what we're talking about. Okay, or triangle, triangular cylinder, whatever. That's what this trigonal planar geometry looks like. All right, when we actually do it with a Lewis dot structure. Okay, so ammonia is an example of a trigonal planar molecule, and would look like this. Okay, so in a trigonal pyramidal, not planar, trigonal pyramidal, we're going to have, again, 3 sides that are bonded to some other atom, and then we have our lone pair on top. Okay, so that's what it would look like in a Lewis dot structure. And again, the bond, because we have 4 domains, that bond angle is still 109.5, or super close to it. Okay, so the last type of shape that we're going to study at this intro level is what we call the bent geometry. And again, this comes from the center atom still having 4 electron groups or 4 domains, 4 sides with electrons, but now 2 of them are bonded and 2 of them are lone pairs. So water is actually a perfect example of this, right? We have oxygen in the middle, right? Oxygen has 6 valence electrons, bam. And then these other 2 pairs of electrons are going to be shared with hydrogen to make bonds, right? So in this case, we've got 1, 2, 3, 4 sides with electrons. So we still have the 4 electron groups or domains around that center atom, but 2 of them are lone pairs, meaning they're not going to form a bond, and 2 of them are bonding pairs, meaning that they do form a bond. Okay, and so in this shape, we can even see it in our Lewis dot structure that it literally looks bent. Okay, so we call this the bent geometry. Now, if we take into account all of the domains, okay, even the bonded pair and the lone pairs, that angle is still about 109.5. Okay, because again, we still have 4 groups of electrons surrounding that center atom. All right, so the bond angle is technically still 109.5, even though when we take a look at the actual, picture or model, the space filling or, actual like ball and stick model, we don't see, those bonded pairs on top. So this angle here is still 109.5. Okay. All right, so on this, down here, this picture at the bottom, we can see that there's lots of different types of molecular shapes. We went over the 5 basic, but there are other shapes like trigonal, bipyramidal, and octahedral, where, it gets a little bit more complex. But we'll leave that for higher levels of chem. All right, so what I want you guys to do is go ahead and write these down on your papers. Okay, so this is PECL with the little 3 there. All right, and this is chlorine and then NO. All right, and I want you guys to pause and then draw the Lewis dot structures and figure out what shape these guys are. And then you can click play, and we'll go over the answers together. Okay, so let's take a look at the first one, PCl3. So we have phosphorus, who we're going to start with, because remember, he makes the most number of bonds. So phosphorus has 5 valence electrons, and so we're going to put his 5 valence electrons around him. And then we've got him hooking up with 3 chlorines, and we've got 3 empty spots here, 3 unpaired electrons around this center atom. So we're going to put a chlorine at each of those spots, and chlorine's going to bring one of his electrons to share. Right, and he's got 6 other paired electrons around him. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. All right. So taking a look at this molecule, we've got 1, 2, 3, 4 electron groups, right, or 4 electron domains. We have 3 bonded pairs and 1 non-bonded pair. All right, the one on top is not making a bond. So the only shape that goes with this kind of combination of electron domains and bonded versus non-bonded pairs is our pyramidal. The trigonal pyramidal. Okay, so that's the shape for this one. So trigonal pyramidal. That's the shape for PCl3. So it's going to look like if we draw it out, it's going to look like a triangle with, the top or the center atom kind of popped up a little bit. It's not going to be flat like the trigonal planar. Okay. All right, let's go ahead and take a look at ClNO. All right, so we have chlorine, nitrogen, and oxygen. And between these three, nitrogen is going to make the most number of bonds. So we're going to start our Lewis dot structure with nitrogen. Remember, if we look at the periodic table, right, on the very right-hand side are our nonmetals, and the noble gases are to the very, very right-hand side. They make no bonds. And then the one just to the left of them are the halogens, like chlorine, that make one bond because they just need one more valence electron to fill their shell. And then the column number 6 to the left of that needs 2 electrons to fill their shell. And then the column to the left of that, all right, the nitrogen group column, needs 3 electrons to fill their shell. So nitrogen is going to need 3 electrons more to fill his shell because he's got 1, 2, 3, 4, 5 valence electrons of his own. Okay, so we always start with a guy that needs to make the most number of bonds. So that's why nitrogen's in the middle. And then we're going to do the atom that makes the second most number of bonds. So that's going to be our oxygen. So oxygen has 1, 2, 3, 4, 5, 6. Okay. And then we are going to put our chlorine. All right. And typically I just kind of want to place them around that center atom. We may have to, move the chlorine down to oxygen if need be, but it's kind of just trial and error until we get it figured out. Okay, so there's chlorine with his 7 electrons, valence electrons, I should say. All right, and so in this Lewis dot structure, we should actually have a huge red flag for this, right? Big red flag, because what do we see? We see unpaired electrons. We see 2 unpaired electrons here, which is a big no-no. Remember, everybody has to be paired up. So we've got nothing else to add according to our chemical formula. So that means that we need to basically bring these 2 guys together to form a double bond between nitrogen and oxygen. So let me erase these 2. And then I'm going to put the dots in between nitrogen and oxygen to form that double bond. Okay. All right, so here's our molecule. And this one is actually, this one's actually a little bit trickier because we didn't really talk about this rendition. So I'm glad this is an example. But we've got how many electron domains? All right, we have 1. First of all, it's always centered around the center atom. The center atom here is nitrogen, right? So the central atom is nitrogen. And so when we're talking about shapes, we always have to talk about, or talk about them in terms of the center atom. Now, some molecules are really big, and so they're going to be multiple center atoms. So you have to do the shape around all of those central atoms. You're going to see that in lab number 11 that we're going to do, where you guys will be drawing Lewis dot structures for simple compounds and then more complex compounds. And the more complex you get, you're going to have to make sure that you have multiple shapes depending on what's happening around all of the center atoms. Okay. So in this case, though, nitrogen is our central atom, and we have 1, 2, 3 sides of nitrogen, right, that have electron domains. So we have 3 electron domains or electron groups around nitrogen, right? But one of them is a non-bonding pair, right? And then 2 of them are actual bonding to other atoms, right? So one of them's to chlorine, the other bond to oxygen there, okay? All right, so remember, these guys want to take up, an equal amount of space, all right? So this guy's going to take up space, that guy's going to take up space, that guy's going to take up space, okay? So earlier we talked about 3 domains being the trigonal planar. And if there was another atom bonded right here, then it would be a trigonal planar. But since there is not, there's actually no atom there, we're going to call this bent. Okay, this is a bent shape. It doesn't look like that on paper, but this guy is going to literally like bend these down a little bit. So in reality, it's going to look like that. Okay, with, you know, his lone pair here going, ha ha, move away, you suckers. All right, so yeah, so it's going to be a bent shape. Okay, so add that to our list. Bent can have, well, before we said it has to have 4 electron domains, 2 bonding, 2 non-bonding. We can also have a bent shape where we have 3 electron domains, 1 non-bonding, and 2 bonding. Okay, so same type of shape, okay, but just a little bit different in how this shape is determined. All right, so that's our bit about the shapes. We just do the 5 simple ones: linear, trigonal planar, tetrahedral, trigonal pyramidal, and bent. Okay. Now we're going to take a look and shift gears to the concept of polarity. Okay, so polarity, we can't talk about polarity until we talk about electronegativity. And that's something that we hammered a lot in regular chemistry. So hopefully that term, you know, you still remember or it's familiar to you. Electronegativity is the ability of an atom to attract electrons to itself. Okay, so basically it is the ability of one atom to attract electrons from a different atom to itself. Okay, so if you guys remember on our periodic tables, the nonmetals, okay, have very high electronegativity. They are very good at attracting other atoms' electrons to themselves. So that's why when a metal and a nonmetal hook up, the nonmetals are the ones that are gaining the electrons because they have got very high electronegativity, right? But when 2 nonmetals are, looking to bond, they are going to be sharing their electrons because both of them are going to have high electronegativity. And so they're not going to be, neither of them is going to concede their electrons. So they're just going to kind of share or fight over the electrons as they make that bond. Okay. So let's take a look at the molecule water, H2O. In this molecule, oxygen is a very highly electronegative atom. All right. And I either have or I will put up on Canvas the electronegativity kind of chart for the elements on the periodic table. Okay, so I've got a periodic table that has little electronegativity values in the lower right-hand corner of each element box. I'll put that up or a actual chart of electronegativity so you guys can reference that. But looking at that chart, you're going to see that oxygen has an electronegativity value of 3.5 and hydrogen has an electronegativity value of 2.1. Okay, so hydrogen's fairly, strong, but oxygen is definitely stronger. And so this oxygen is more electronegative. So that means even though they're sharing electrons because they're both nonmetals and they're making a covalent bond, more electrons are likely to be found near the oxygen than the hydrogen. So what that means is that oxygen is an electron hog, I like to call them, right? So they're sharing electrons, but they're not sharing fairly. Oxygen is hogging the electrons more than hydrogen. Okay, it's kind of like, you and a younger sibling and you're like, quote unquote, sharing the Nintendo Switch, right? And you're like, well, I can play with it for 10 minutes and then my little brother can play with it for 5 minutes and then I get it back and I can play with it for 10 minutes. You're technically sharing, but you're not sharing fairly since your little brother is getting gypped by 5 minutes, right? That's kind of what's happening with our electrons in this molecule. Oxygen is the big brother who's getting to spend 10 minutes with the electrons, while hydrogen is the little brother who gets to spend only 5 minutes with the electrons. They're sharing, but not fairly, okay? So this is going to set up a molecule where the oxygen is going to have the electrons more, for a more period of time. So the oxygen is going to have what we call a slightly negative charge, and the hydrogens are going to have slightly positive charges, okay? And this little it's a lowercase delta, but it's it conveniently kind of looks like a fancy S. So I call it the S for slightly. Okay, so it is not a full charge like when a metal and non-metal hook up and the non-metal fully gives away its electron to the metal fully gives away its electron to the non-metal. It's not like that. Remember, in covalent bonds, the non-metals are both fairly high in electronegativity and they're sharing their electrons. Okay, so these are going to be slight charges and not full charges, like in ionic bonds. All right, so since the electrons are unequally shared, the oxygen atom has a partial, okay, or slight, call it partial or slight negative charge. And then the hydrogen has a partial or slight positive charge. And this is what sets up what we call a dipole moment. Okay, so this is just a fancy word that means a molecule that has a slightly negative end and a slightly positive end. Okay, a dipole moment. So back in regular chem, you might remember us talking about polar versus nonpolar covalent bonds. So we call these covalent bonds that have a dipole moment, or a positive end and a slight positive end and a slight negative end. We call them polar covalent bonds, right? So polar means they are not sharing fair, right? So not sharing fair, and covalent just means they're sharing, right? So I guess another way we can think about it is the polar part just means not fair, and the covalent means sharing. So not fair sharing, right? And when we're talking about bonds, we're talking about electrons. So electrons that are being shared non-fairly. So this degree of polarity of a bond is going to depend on the difference in electronegativity between the two elements. So here, this big chart is a chart of electronegativity values for every single element. So you can see over here on the very left-hand side, these are metals, and they have very low numbers compared to the right-hand side, which are all non-metals. And remember, hydrogens are non-metal too, so that's why he is a 2 over there, 2 point something rather than a 0, 1 point something. Okay, so the further you are to the right, the stronger electronegativity. So the greater the bond means the greater the dipole moment, which is more polar. All right, in fact, in regular chem, we did talk about the difference in electronegativities, and we did calculations, and we had some, like ranges, okay, numerical ranges that denoted, which was nonpolar covalent, which one was polar covalent, and which one was ionic, right? So if two elements have basically either identical electronegativities, or the difference in electronegativity is between 0 and 0.4, okay, that means they are sharing equally. They are sharing those electrons equally. All right, so that means, big brother's being nice to little brother today, and they both get 10 minutes on the Nintendo Switch, right? And nobody's hogging it. So in this case, we're going to see in these pictures that we have no positive or negative ends, because there's no dipole moment being made, because everybody is sharing equally. The electrons are not being hogged to one side or the other in these types of molecules. So that's why we call these types of molecules non-polar, because there's no poles or no positive or negative ends on these molecules. So anytime you have a bond between two elements, you have to take a look at the difference in electronegativity. So use the chart, and if your difference in electronegativity is between 0 and 0.4, we usually have one that, like a chart that is just one decimal. But if you're using a chart with 2 decimals, we're going to say 0.49. Okay, so 0 to 0.49. All right, then those two atoms are sharing their electrons equally, and that is what we call a non-polar covalent bond. All right, so No positives or no negatives, no slight charges at all in nonpolar covalent bonds. Now, if we find two elements that have kind of intermediate electronegativity differences, meaning that if we subtract their electronegativity difference and we get a number between 0.5 and 2, okay, that means that they are sharing unequally. So this is where the big brother is being a hog over the electrons than the little brother. All right, kind of like what we talked about in the water molecule a couple slides ago. So this is going to set up positive and negative ends. But remember, these guys are slight positive and slight negative. They're not full charges. Okay, so like over here with the little s's, slight positive and slight negative charges. That's what we call a dipole moment. And these types of bonds are what we call polar covalent bonds. Okay, so polar covalent bonds have these slight positive and slight negative charges on the ends because of a unsharing of electrons between the atoms that are making the bonds. Okay, so in order to figure out if an entire molecule is polar, because remember, we're just talking about bonds right now. So when you're figuring out if an entire molecule is polar, you actually have to look at every single bond separately, see what's going on, and then take a look at the overall shape as well. Okay, so just keep in mind that we haven't gotten to the molecular level yet. We're just looking at the bonds right now. Okay, so molecular polarity will depend, okay, on the shape and what's going on with these polar covalent bonds. All right, so let's take a look and see what happens with elements that have a very large electronegativity value, or difference, I should say. So if you subtract the electronegativity values for two elements and you get a difference of 2 or greater, right, then that means there's a very large electronegativity difference. One is pulling much harder or attracting those electrons much more than the other. In fact, so much that we get a transfer of electrons. Okay, so they're not sharing anymore. One is totally giving up the electrons to another. So this happens in ionic bonds, right? So this is where we're going to have a metal atom and a non-metal atom, right? And if we look at the values, right, these electronegativity values on the non-metal side are fairly high. The electronegativity values on the metal side are very low. And so most of the time we're going to get a difference of 2 or greater. In which case, what this literally means is that fluorine's attraction is so strong, it literally rips sodium's valence electron away from him. Right? When they do that, they become full charges, right? Sodium's going to have a full +1 charge. Fluorine's going to have a full -1 charge, and opposites attract, and that's how they stick together. So that's ionic bonding. However, this chapter we're going to focus mainly on nonpolar and polar bonding and the covalent bonds, because that's going to help us set up the different shapes that we're going to see in covalent molecules. All right, so now you guys are going to pause for a few minutes and do some practice with this and see how well you guys understand. So for each of these pairs of atoms, you guys are going to subtract the electronegativity values using the chart on the screen and classify each pair of atoms as being bonded together by pure covalent, which means non-polar. So actually I should say non-polar covalent bond, a polar covalent bond, or an ionic bond. Okay, so go ahead and pause it, do the math, and figure out the bond types, and then you can unpause it and I will go over the answers together. Okay. All right, so let's take a look at strontium and fluorine first. So fluorine has a electronegativity value of 3.98. Strontium, which is here, is 0.95, right? So when we take a look at that math, we end up with a difference of 3.03. Now that falls in our ranges, in that range of 2 or above. So this is an ionic bond. So SR and F make an ionic bond. And in this case, fluorine is so electronegative that he is going to literally rip away strontium's valence electrons and hog them to himself. And so fluorine's going to have a full positive charge, and strontium's going to have a full, fluorine's going to have a full negative charge since he's got the electrons, and strontium is going to have a full positive charge since he lost his valence electrons. Okay. All right, let's take a look at the second one. This one is nitrogen and chlorine. Okay, so chlorine is 3.16. Nitrogen has a value of 3.04. So when we subtract those, we get a difference of 0.12. And that falls under the nonpolar, right? Remember, nonpolar is 0 to 0.49. 0.12 is in between, so that is definitely a nonpolar covalent bond. So what that means is that when nitrogen and chlorine hook up and share electrons with each other, they're sharing fairly. Okay, so neither is hogging the electrons more than the other. Okay, last but not least, let's take a look at chlorine again and carbon. So we're going to do 3.16 minus 2.55. So here we're going to have a difference of 0.61. So that falls under our second category of 0.5 to 2. This is our polar covalent bond. So that means when carbon and chlorine hook up, they are not going to share fairly. Chlorine is going to hog the electrons from carbon. And so chlorine's going to have a slight negative charge, and carbon's going to have a slight positive charge because chlorine is not sharing fairly. All right. Now is where we're going to start melding the two ideas together. We started with molecular shape, and then we diverged into bond polarity. Now we're going to put the two together to figure out molecular polarity. Okay, so the shape, the polarity of the entire molecule. All right, to see if the whole molecule has positive ends and negative ends, not just the bonds that make them up. So the presence of one or more polar bonds in a molecule does not always result in a polar molecule. You got to think about that. So just because you have a polar bond in a molecule does not mean the entire molecule is going to be polar. Sometimes they can cancel out and be nonpolar. All right, so this is where it gets a little tricky. So make sure you kind of understand, pause, go back, or read the section in your textbook real carefully, and then make sure you ask any questions that you have. Okay. All right. So a polar molecule is one with polar bonds that add together to form a net dipole moment. Okay. That means that basically the polar bonds do not cancel each other out. So we're going to get one side of the molecule that has a positive end and one side that has a negative end. Okay. So polar molecule is going to have polar bonds that don't cancel each other out. So we're going to have one side, right, of the molecule slightly positive and the other slightly negative. Okay. So let's take a look at two examples. So we've got water molecule on the left here. Right here, we got a water molecule. And if we take a look at the bonds, okay, so anytime you have to figure out the polarity of a molecule, you have to look at the polarity of the bonds first. So between oxygen and hydrogen, if you do the electronegativity difference between them, you're going to get a difference of 1.4. Okay, so what that means is that oxygen is pulling on the electrons harder than hydrogen, right? They're not sharing fairly. This is a polar covalent bond. So we've got polar bonds in this molecule. So in order to see if this entire molecule is now polar, we have to look at the direction of how these electrons are being pulled. So in the water molecule, the oxygen is hogging the electrons from both of these hydrogens. And because it is a bent shape, okay, basically all of the electrons are spending more time at the top of this bent shape than they do at the bottom. Okay, so this means that these polar bonds are all pulling up towards oxygen, so they're not canceling each other out. So therefore, we've got the oxygen side of the molecule that's slightly negative and the hydrogen side of the molecule that's slightly positive. So this ends up being a polar molecule because the pull is not in opposite directions. It's in the same direction. They're both pointing towards oxygen. Okay, so if the polar bonds don't cancel each other out, it is a polar molecule. Now, the second picture here is carbon dioxide. And if we take a look at the polarity difference of the bonds between carbon and oxygen, we're going to find again that these guys are polar bonds. Polar bonds mean that oxygen, in this case, is pulling harder on the electrons and not sharing fairly compared to carbon. All right, but in this molecule, this is a linear shaped molecule. And so we can see that the oxygens are pulling in equal and opposite directions. So the oxygen's over here, this is a negative side, all right, and then this is a slight negative side, and then we have a slight positive in the middle, all right. So there's not one end that's positive or one end that's negative. Both ends are negative and the middle's positive. So in this case, because we don't have, a specific end that's positive and a specific end that's negative, we call this a non-polar molecule. Or another way to determine that is looking at the direction of pull on these electrons. They're pulling in equal and opposite directions, right? So this the oxygen on the left is hogging electrons towards the left side. The oxygen on the right is hogging electrons towards the right side. They're pulling carbon's electrons in equal and opposite directions. So that means they cancel out and we get a non-polar molecule. Okay, so here are some things to keep in mind when thinking about molecular polarity. So like we mentioned before, the presence of one or more polar bonds, right, in a molecule does not always mean that it's going to be a polar molecule, right? If those bonds pull in equal and opposite directions, they'll cancel out and the molecule overall would be non-polar. Okay, so typically symmetrical molecules are going to be non-polar because their polar bonds are going to cancel out. All right, asymmetrical molecules are typically polar. Okay, if they've got polar bonds in an asymmetrical molecule, then it's typically a polar molecule. But like I said, you have to look at the bonds, all right, the bond types of each bond in the molecule. You gotta, it's super easy to draw the arrows, right, towards whoever is hogging the electrons. And then if those arrows are canceling out, it's nonpolar. If the arrows don't cancel out, then it's definitely a polar molecule. Okay. So to determine whether a molecule is polar, first, determine whether the molecule contains any polar bonds. And then second, right, determine whether the polar bonds add together or cancel out. If they add together, then it's going to be a polar molecule. If they cancel out, it is nonpolar. So let's take a look at this example here. In fact, I'd like you guys to do this on your own. So for figuring out if a molecule is polar or nonpolar, if I just give you the molecular formula like this, NH3, first thing you have to do is draw the Lewis dot structure. Okay. From there, look at each of the bonds and subtract the electronegativity values. Determine if the bonds are polar or nonpolar. Then after that, draw arrows to show, if it's a polar bond, draw arrows to show who's the electron hog. And then finally, look at the arrows and see if they are pulling in equal and opposite directions, or if they're all adding, together towards one direction. So go ahead and pause and do this for NH3, and then you can unpause and I'll go over it with you. So for NH3, we've got nitrogen, who has 5 valence electrons, and he's going to be hooking up and sharing those lonely electrons with hydrogen's lonely electrons, right, to make covalent bonds here. Now, if we take a look at the electronegativity difference, right, for nitrogen, nitrogen's 3.0, hydrogen is 2.1. So if we subtract that, we get a difference of 0.9, right, which is in the polar covalent range. So that means that when they're sharing these electrons, nitrogen is pulling the electrons more, or hogging the electrons more than hydrogen. Okay, so to depict that, we're going to draw arrows towards the nitrogen. So when we take a look at this overall molecule, we can see all of the arrows are pointed towards nitrogen. So nothing is pulling in opposite or equal directions, and so this is definitely a polar molecule overall. So these polar bonds added up to be a polar molecule overall. All right, so my suggestion is to definitely use the textbook and go over many, many more examples of this just to get yourself familiar about how to do it. So please, use that as reference and get, familiar with figuring out the shape and polarities. Now, why is this important? Well, because we can see how different molecules behave with each other in terms of polar molecules versus nonpolar molecules. So they're going to behave differently. Polar molecules are going to interact strongly with other polar molecules. They've got the positive and negative ends that are going to be able to attract to each other. So polar molecules will be able to mix with other polar molecules. Okay, because their positive and negative ends will attract each other, and they can kind of, mingle and float around with each other. However, if nonpolar molecules are around any polar ones, they're not going to be able to stick to the polars, right? So polar and nonpolar molecules don't mix. In fact, in regular chemistry, we call that the like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar, because nobody has any charges, so they can mingle with each other, right? But as soon as we mix polar and nonpolar, because polar has charges and nonpolar doesn't, they're not going to mix. Polar is not going to be able to grab onto any of the nonpolar molecules and mingle with them. So they're going to separate. So a classic example of this is oil and water. So if you have a salad dressing made of oil and water parts, you'll see it's separate in the bottle. You got to shake it up, right, in order to get them kind of dispersed in each other. But if you let it go and you set it on the table, you're going to see they're going to separate again. All the polar water-based molecules are going to find each other and stick, and all the nonpolars are going to be pushed out because they have no positive and negative ends for the polar molecules to stick to. So it's kind of a neat feature that is explained by polarity and electronegativity.